Hi everyone, welcome back. Just a quick reminder that in this channel, I post videos about statistics, data analytics, and machine learning. Now, this is one of my videos about statistics. And specifically, I will show you in this video how to use R to do a correlation analysis as part of the preliminary steps that we need to take before doing a regression analysis. Okay, so my end goal with the data set that I will be using in this video is to do a regression analysis. But in this particular video, I won't do that regression analysis. I will focus on the correlation analysis that is recommended to do prior to applying regression. Okay, but definitely stay tuned to the video about regression. Okay. All right. So I prepare a notebook to do this video. And as usual, I will share a link to this notebook in the video description. All right. Okay. So let's go. So this is the notebook I prepared for you guys. And let's start by, as usual, um, loading or installing the packages that we need. Okay. The external packages that we need. In this video, we only need to use two external packages, the ISLR package, this one right here, and the tidyverse package, okay? But the ISLR package, we need to install it, okay? We need to install it. And I already installed it, so I don't need to install it in this video. But if you're gonna use this notebook, you need to install it, okay? In case you don't have it. And this is the code that will allow you to install the package. Okay, so when you are going to use this notebook, you need to remove the comment from from that line of code. Okay, and then go ahead and execute the code cell, and the ISLR package will be installed. Okay, but again, I don't have to do it because I already installed it. Okay. What I need to do is load it. Okay, remember, for every external package, after you install it, you need to load it. Okay. And to load a package, remember that we use the library function, okay? So let me go ahead and, load the package. And I will also load the tidyverse. I always load the tidyverse package because it's very useful for doing manipulation, data transformation. It's so much easier to use the tidyverse functions that regular base are functions, okay? So really, really like the tidyverse. Now this package, why do we need this one? Because we know why we need the tidyverse, but why do we need this one? Because the data set that I will use in this video is part of that package. The ISLR package contains a few data sets, and we're going to use one of those data sets, specifically the credit data set. Okay. And once we load a package, the data sets that come with that package gets loaded automatically, so they become available for us to use. Okay, so right now, after I loaded this package, I can just go ahead and start using the credit credit data set just by typing its name. Okay. All right, so I'll explore. Let's go ahead and explore quickly the credit data frame. Okay, which, as I said, is the one we're gonna use here. And the only thing we need to use is just, type in its name, because after loading the package, it becomes available. Okay. Let's take a look at the column names from that data frame. This data frame is about people's kind of credit card information, okay, or credit profile, if you will. Okay. So we have data about 400 people, and for each person, we have information about um, his or her income, the credit card limit, the credit rating, number of cards, the age, the education level, gender, student, married, ethnicity. These are kind of categorical variables, those four. And we have the balance, okay? The balance is the credit card balance, okay? The credit card balance, and that's actually the outcome variable that we're gonna target in our regression analysis, okay? So what is the goal? What is the specific goal with this data set? Well, we want to obtain a good multiple linear regression equation to predict the variable balance based on all other available columns. Remember, I said that my end goal here is to apply regression, which I will do in a different video. And in that regression analysis, my outcome variable will be balance, credit card balance, this column right here. And I'm going to use all the predictors, all the columns as predictors, okay? All right. There are two columns here that I know I don't want to use in my regression analysis, so I'm just gonna go ahead right now and remove them. And they are ID and ethnicity. ID is just because it's irrelevant. The ID column records the row name. The row name is irrelevant in a regression analysis to predict balance. So I'm gonna remove ID because of that reason, and ethnicity just because it might be unethical, I think, in my opinion, to include ethnicity when you want to predict balance, okay? So it might be considered unethical. So I prefer to remove it, okay? And that's what I do next. All right, I remove ID and ethnicity, and to remove them, this is the code I used. I said, all right, from the credit data set, select everything but ID and ethnicity. How do I tell R that I want to select everything but ID and ethnicity? I use a negative sign before the names of ID and ethnicity. So when you use negative sign before a column, that column gets excluded from the select result, okay? So basically this is going to select every column in this data frame but ID and ethnicity, okay? And notice that I am assigning, this is the assignment operator, I am assigning back the result of this to a new data frame. So I want to have a new data frame for my kind of modified data set, okay? And the title I use for this new data set is credit DF data frame BSS. Why BSS? Because, as I said, I will eventually apply regression, and I will apply regression using a method titled best subset selection. So that's why I use this abbreviation here, BSS, okay? All right, so let me go ahead and execute this code cell. And now let's take a look at this new data frame using the structure function. Structure function gives us a kind of a summary of our data frame. And there we have it. So we don't have ID and ethnicity anymore. And we can see here that we have data about 400 observations, so 400 people. And for each person, we have, as I said, all of this information, okay? Okay, so now remember, the goal of this video is to do a correlation analysis, okay? And what I want to do is first, I want to do a correlation analysis between the quantitative predictors and the outcome. And then I will do a correlation analysis between the qualitative predictors and the outcome. Notice that three predictors, these three, gender, student, and merit, they have factor data type. So they are categorical or qualitative. They are not quantitative. Whereas the rest, income, limit, rating, they are either numeric or integer, okay? So I want to split the correlation analysis in two steps. So correlation between quantitative predictors and the outcome, and then qualitative predictors and the outcome, okay? And that's what I'm gonna do. That's what I'm gonna do right here. Correlation between the quantitative predictors and the outcome. But first, I want to show you how to use code to retrieve the quantitative predictors. In this specific data frame, it's not hard to see that the quantitative predictors are income and limit and rating, cars, age, education. So it's just a few because, you know, this data frame is very small. But in a larger data frame with more columns, so it might be a little bit convoluted to find out what are the quantitative predictors. So I'm gonna show you how to use code to do that, okay? And that's what I'm doing. I'm trying to use code to retrieve the quantitative predictors. And what I do is I said, all right, from the data frame, select, and then inside the select function, I wrote that expression right there, right? That expression right there. That's what I wrote inside the select function. What does that expression do? Well, I'm saying select any column where the type is integer, or that vertical line is the logical or in R. So where the type is integer or numeric, okay? So where is just a utility function that is used in combination with select. Okay, so where is a kind of auxiliary function that you can use together with select to select the columns based on different Boolean conditions. Okay, in this case, the Boolean condition is regarding the data type in the column. Okay. So, all right, so where the data type is integer or numeric, I want to select. So if the data type of the column is integer or numeric, I want to select it, otherwise I do not, okay? And that basically will select everything but these three columns, the factor data types, okay? The ones that have a factor data type. And the last part, let me comment out the last part for a second. So let's execute this part. It looks like it works, right? So I'm only selecting the quantitative columns. So I don't see any of the factor data types columns here. Okay, so it works. But the last part is just because notice how balance was moved to the second to last position. Originally, balance was the last column, but now it was moved to the second to last position, and I don't like that. It's not wrong. It's okay if you leave it like that, but I prefer to have balance um, in the last position because of something that I'm gonna do next. Okay, so I prefer to have balance in the last position, and that's why I'm using relocate. Okay, relocate. And relocate, what do I want to relocate? Balance. Where do I want to place balance? After what column? After the last column. That's a utility function. Last underscore COL parentheses that allow us to retrieve the last column without mentioning its name. So you don't need to mention the name of the column. It will just retrieve the last column. Okay, so it's very convenient. And let's go ahead and execute this. And sure enough, now balance is the last column. Okay, perfect. The next step is to compute the correlation between between these quantitative columns. And the correlation is actually the correlation coefficient, the Pearson correlation coefficient. Okay, lowercase r. And to compute the Pearson correlation coefficient, I'm going to use the function COR, okay? So what I'm going to do in the next code cell is I'm going to repeat that code right there, and I'm gonna apply the correlation function on that piece of code, okay? And here we are. That is, this is the code from the previous code cell right there, okay? And what I did was I applied the COR function, correlation function um, to that piece of code. And one more thing I did, I store the result of that in something in a variable that I call correlation matrix credit. I call it correlation matrix because the result of correlation is actually a correlation matrix. So it will show us each the correlation between each pair of quantitative columns. Okay, so let's see our correlation matrix, and let's take a look at it. And there we have it. Okay, so we see the correlation between each pair of quantitative columns. All right, and just a reminder that the correlation coefficient is a number between -1 and 1, and then remember that the closer in absolute value to 1. Okay, so the closer in absolute value to 1, that's an indication of that the correlation is stronger. So the closer to 1 in absolute value, the stronger the correlation between the variables. And the closer to 0, the weaker the correlation. Negative correlation means that the variables have a negative association. Positive correlation means that the variables have a positive association. Okay. All right, from that matrix, I want to kind of split the analysis in two parts. First, I'm going to focus on the correlation between the outcome, balance, and the predictors. And for that, I'm going to look at the last column. So when I explore the last column, I can see that most correlations are small. Okay, so like this correlation between balance and cars, very small, okay, very close to zero. Balance and age, very close to zero, and balance and education, very close to zero. Um, but I see that at least two correlations are kind of high, right? So the correlation between balance and limit, 0.86, 16, and the correlation between balance and rating, 0.86, 36. Okay, so the correlation between balance and limit, balance and rating are high. And then I can also see that the correlation between balance and income is not very low, but it's not very high either. It's kind of a moderate to weak correlation. Okay. And yeah, that's what is worth mentioning in from that analysis. So, like, what are the predictors that show a correlation with the outcome? Limit and rating for sure, and income to a certain extent. Okay, and that's what I wrote for you guys here. Okay, correlation with the outcome. With the outcome should be singular. Correlations with the outcome. Um, Limit and rating are the predictors with the strongest correlation with balance. They are both positively and strongly correlated with balance. Okay. Why strongly? Because their correlation is kind of close to one. Okay. 0.86. So what does that mean? What is the meaning that limit is strongly and positively correlated with balance? Well, it means that um, the higher someone's credit rating, okay, the higher someone's credit rating, the higher his or her credit balance. Okay, so it looks like people with higher credit rating spend more. Okay, have a higher balance. Okay, and the same thing with limits. So people with higher credit limit have a higher credit balance. Okay, so that's what is going on in that case. That's good to know. And in terms of income, what I said was, income has a weak to moderate correlation with balance, but at least it is worth mentioning the correlation between income and balance. But the other predictors, cars, age, education, they do not exhibit a correlation with balance. The correlation coefficient is very, very close to zero. Okay. That's good. One thing that I want to do whenever I compute the correlation coefficient, I like to pair the correlation coefficient with a scatter plot as a kind of confirmation. Okay, so I want to do a scatter plot between limit and balance, rating and balance, and income and balance to kind of confirm that the correlation is indeed strong or weak. Okay. And that's what I'm doing with this code, okay? To do the scatter plots, I'm using ggplot, the ggplot function from the tidyverse. And I'm saying, well, I'm passing 3 arguments to ggplot first, the data frame that we're using. And then I'm telling to ggplot, hey, map the income from this data frame, map the income column to the x-axis and map the balance columns to the y-axis. Okay, but actually, you know what? I don't want to show income first. Let me do limit. Okay, let me do limit rating and then income. Okay, so I'm gonna map limit to x, balance to y. All right, and the geom the geometric shape that I want to use is points. So geom points. So whenever you want to do a scatter plot, the geometric shape that you should use is geom point. Okay. If you're using a different type of chart, like a bar chart, box plot, you need to use a different geom. Okay. But in this case, geom point. All right. So and what do we see here? That's the scatter plot between balance and limit, and we confirm that they are strongly correlated. So we can see a very, very clear uh, upward trend, right? So very clear upward trend. So definitely, so we confirm that the correlation is high, okay, as we saw here in the correlation coefficient. Now let's do it between rating and balance. One more time, we confirm strong positive correlation. And between income and balance, now we should see a kind of weaker correlation, okay? And we do, but I want to point out that we can still see a kind of upward trend. Look at the cloud of points. In general, the cloud of points seems to go up, like a kind of an upward trend, okay? But the correlation is weaker because there is a lot of variability. The data points are all over the place, so there's a lot of variability around the relationship between balance and income. So notice that, I don't know, for example, look at this area of the chart. We can see that, people with low income, some people have low balance, okay, but some people with low income has a high balance, like this area right here. These are people with low income and high balance. So that kind of contradicts mm, um, the positive relationship, right? Because people with low income should have only low balance, okay? And then kind of here as well, look at this area. Here we can see people like specifically this area. These data points right here, they correspond to people with high income but somewhat low balance. You know what I mean? So there's a lot of variation. So we see a kind of upward trend, but a lot of variation around that pattern. Okay. So we confirm that the relationships suggested by the correlation coefficient actually exist. Okay. Cool, guys. With this matrix, we can also explore the correlation between the predictors, okay? So if we look at these columns right now, so the columns representing the predictors, we can use that information to detect pairs pairs with high correlation, okay? And why is that important? Because remember, in regression analysis, there is something called collinearity. So which means two predictors with a high correlation, okay? So we want to detect two predictors, we want to detect predictors that possibly have a high correlation, okay? And remember, collinearity is problematic in a regression analysis because remember, in a regression analysis, the end goal is to obtain a regression equation. In that regression equation, you're going to have coefficients. So each predictor is going to have a coefficient, right? Well, guess what? When two predictors have a large correlation, okay, between them, the coefficients in the regression equation are bad estimations of the real coefficients. So the coefficients that you get for predictors with high correlation with each other, they are bad coefficients. So they are bad estimations. They are not accurate estimations. They are kind of really far from the real values of the coefficients. Okay, so that's why whenever you detect predictors with high correlation, you should be aware of that and take care of that, okay? And the usual, not the only, but the usual way of taking care of that is by removing some of the predictors. So if you find a pair of predictors with high correlation, you remove one of the predictors from the pair, okay? Okay, and that's what we're gonna do here, okay? Um, so the criterion that I'm going to use is, the kind of most widely used criterion, which is kind of, an oversimplification, but it's okay. It's okay. It's not bad. It's kind of oversimplified, but it's okay. And the criterion says that whenever the correlation between two predictors is 0.70 or more in absolute value, so whenever the correlation coefficient between two predictors is greater than or equal to 0.70 in absolute value, that is a sign that the predictors are collinear. And then the usual step after that is to remove one of those two predictors. Okay. So when you look at those columns, you notice that here we have a correlation of 0.99 between limit and rating, way above 0.70. All right. And here again, we see the same correlation. So remember, correlation is symmetric. So correlation between X and Y is the same as the correlation between Y and X. So uh, this is just the same value repeated. Just a correlation between limit and rating. Huge correlation, 0.9968. And we also see, if we keep exploring, we also see that limit and income has a high correlation as well, 0.7920, and rating and income has a high correlation as well, 0.7913. So those are the three correlations that are kind of large and significant for the predictors, okay? So what do we do in that case? Well, we can do many things. I'm going to tell you what I did. This is obviously a problem. This is obviously a problem, guys, okay? So a correlation of almost 1 between two predictors, well, that means that those predictors are almost redundant, okay? Because the correlation is almost perfect. So they are redundant. We don't need them both in the equation and in the regression equation. And again, if we try to include them both, their coefficients will be really, really poorly estimated, okay? So we don't want to do that. We need to remove one of them. And what I did was I removed limit. I removed limit. So I kept rating and I removed limit, okay? You can do it the other way around. You can remove rating and keep limit, okay? But in this case, if you do that, you'll see that in any of those two situations, you're gonna get the same results, okay? Um, but anyway, so I removed limit and I kept rating, okay? And in terms of how about limit and income and rating and income, because they also have a correlation above 0.70. Well, guys, definitely you can make the argument that because the correlation is above 0.70, we should also remove, well, let's not talk about limit anymore because limit is out of the way. So we remove limit. So let's focus on rating and income. Rating and income. What do we do in that case? Well, we can remove one of them, right? So we remove either income or rating. But I didn't do that. Okay, I didn't do that. There is an argument to make that you should do that, okay? Because again, the correlation is about 0.70, but I didn't do that in this case. What I did was I took care of the most obvious problem, the correlation between rating and limit. Okay, that's the most obvious problem, and I removed limit. But definitely, uh, because the correlation between rating and income is also very high, you can also try to remove one of them. And the way of doing this is, let's say you want to attempt this, taking care of removing either income or rating. You remove rating and do the regression analysis, and then you remove income and do the regression analysis, and then you compare the results, and then based on those results, you conclude what is the best one of them to remove, either income or rating. Okay, but again, I'm not gonna do that. I actually kept both rating and income. Okay, all right. So that's what I explained right here. Okay, so what I just said is what I explained right here: the correlation among the quantitative predictors. All right, so you can read all of this once I share the notebook with you. Okay, but basically, the action to take is to remove limit. Okay, notice that again. I'm saying, from this data frame, select everything but limit. So I want to remove limits, and then what I did, I assigned that to a new data frame. So it's credit DF BSS update 1. Okay, so this is our new data frame, the one that does not include limit. All right, and let's execute this, and that's good. So now we don't have limit anymore. All right, perfect. Last step, guys. Last step. Um, we are done with part one. Part one was the correlation between the quantitative columns. Now let's explore the correlation between the qualitative columns and the outcome. We have three qualitative columns: gender, student status, and marital status. And how do we study the correlation between qualitative columns and an outcome and a quantitative outcome? Well, one way is we transform the qualitative columns into numeric ones, okay? So we can create dummy variables from the qualitative columns, okay? And we can use those dummy variables to compute the correlation coefficient, okay? So one way is you take gender and you convert gender from factor data type into a dummy variable, into a 1 and 0 variable, okay? And then you use that dummy and then you compute the correlation coefficient between that dummy and balance, okay? And then you repeat the same for student and merit. That is one way, definitely one way. That's not the way I'm going to use. I'm going to use a more exploratory approach, which is also valid, okay? Which is also valid for sure. What I'm going to do is I'm going to do a box plot, um, just showing the balance for the two genders. So showing me the distribution of balance for the two genders, and that will allow me to see if there is a relationship between gender and balance. And then I'm gonna do the same thing for student and balance, and for merit and balance. Okay, so I'm gonna kind of use an exploratory approach. And I will also use, in addition to the box plot, I'm gonna compute a kind of summary table. So I'm gonna compute the mean, the median, and the standard deviation for each gender, and for each marital status, and for each student status, and that will also allow me to conclude about the possible relationship between the qualitative predictors and the outcome. Let's see what I did here. All right, correlation between the categorical predictors and the outcome. This is just to remind you again what the categorical predictors are, okay? And let's go. Now let's do what I said. Let's do the box plot between balance and gender, and that will be our way of kind of evaluating the relationship between gender and balance, okay? And to do a box plot, we kind of use the same idea we used before for the scatter plot. So we're going to use ggplot, and then we're going to say, okay, from this data frame, map the gender column to the x-axis and the balance column to the y-axis, and then use a geom box plot. So that's the kind of geometric shape that we're going to use, geom box plot, because we want to do box plots, okay? And sure enough, that is gonna give us a box plot for each gender. Okay. Do we see a relationship between gender and balance? Do we see any difference in balance across the two genders? Because to claim that there is a relationship between gender and balance, we should see a difference in balance with respect to the two genders, right? I don't see that right there. The distribution of balance for the two genders seems to be very, very similar. The median seems very similar. Even the quartiles, I mean, they are not perfectly equal, but they are very similar. Okay. And when you compute the summary statistics that I mentioned earlier, okay, using this group by and summarize functions. So let me show you. We kind of confirm that the mean, median, and standard deviation, you can add more summary statistics if you want, okay? I only added 3, mean, median, and standard deviation, but you can add more. But anyway, so I don't see a huge difference between the two groups, okay? So the mean, it's 510 for males, 530 for females, so 20 points of difference, not a big difference. Median's very similar, only 7 points of difference, okay? And the standard deviations are also similar. And again, even in the box plot, the distribution of balance seems very, very similar for both genders. Okay, so I'm gonna conclude that there is no relationship between gender and balance from this exploratory analysis. How about student? We repeat the box plot for a student, and here we see an obvious relationship. Why am I saying that there's an obvious relationship? Because we see that the balance changes depending on the student status. We can claim that there is a relationship between student status and balance because the balance changes depending on the student status. We can see that when for students, the distribution of balance is much higher, right, than for non-students. Clearly see that for students, the distribution of balance is way above the distribution of balance for non-students, okay? The median is higher. The median is, remember, is that black line. Median is higher. The third quartile is obviously higher. The first quartile is obviously higher, okay? So definitely there's a relationship between student and balance, okay? And when we repeat the analysis between marital status and balance, we kind of see same thing we saw for gender, not a clear relationship, okay? So we see that for both married people and non-married people, the balance kind of has the same distribution, okay? And the summary statistics confirm that. So for married people and non-married people, very similar mean, very similar median, and very similar standard deviation, okay? So the only obvious relationship is between student status and balance. All right, conclusions from our regression, I'm sorry, conclusions from our correlation analysis. I wrote the conclusions for you here, guys. All right, first, a rating has a strong and positive correlation with balance as evidenced by the correlation coefficient between them. 0.86. Not only that, rating has the strongest correlation with balance. So the correlation analysis allows us to detect this. The correlation analysis allows us to detect this. We detected what was the predictor with the highest correlation with balance, and that was rating, okay? We also concluded the following. The only other quantitative predictor with the non-negligible, notice that I'm not saying with a large or high, simply non-negligible, okay? The only other quantitative predictor with a non-negligible correlation with balance is income. Income has a kind of moderate to weak positive correlation with balance with a correlation coefficient of 4.8. 0.46. Okay, so all the other predictors have a negligible correlation with balance. Okay, and we also notice this. This is also important to keep in mind once we do the regression analysis. The rating and income, they have a strong correlation. So those two predictors, rating and income, they have a strong correlation, 0.79. Okay, and what does that mean? Well, maybe when we do the regression analysis, since they have a strong correlation, rating and income, they might be redundant. So they might not be both necessary to be in the equation. You know what I mean? So maybe it's not necessary to have both rating and income in a regression equation because they are already very correlated. So maybe the algorithm will find them to be redundant. We'll see. At this point, it's just an speculation, but it's definitely something worth mentioning and worth keeping in mind. Okay. And the last conclusion is that among the categorical predictors, student status shows a strong relationship with balance as evidenced by the marked difference in balance across the two student status. We clearly, and it was very clear, observed that students tend to have a higher balance on average than non-students. So towards our regression analysis, we should keep that in mind, that student status is related with balance. All right, guys. So all of this info, remember, all of this info, we're going to take all of this info with us when we do the regression analysis. Okay, that's what I want to say. We're going to take all of this info, all of these conclusions with us for the regression analysis. Okay, and remember, my end goal is to do a regression analysis, and I will do a video next doing the regression analysis for this specific data set. Okay, so please stay tuned for that video. All right. Okay, that's all for this video, guys. I hope you enjoyed, and I will see you in another video. Thanks.